So my name is Alex Wade. I am on the Chan Zuckerberg Initiative Open Science team. And the format for these demos is going to be roughly 20 minutes, not roughly, precisely 20 minutes per demo. Hopefully we can keep them to 15 minutes of demo, leaving 5 minutes of Q&A for each one of those after. And Ennis, I think you are up with Galaxy.
So as I said, we're during the pitch this morning, we are newcomers to CZI. So this presentation is going to focus about what is Galaxy, the community around Galaxy, and some of the activities we plan on working on during the upcoming year. So while Galaxy is a large collaborative project with many PIs, community members, and stakeholders, for this specific project, I am accompanied by Jeremy Gex from Oregon Health and Sciences University, Nuwan Gunasekara, and Andrew Loney from the University of Melbourne, and Mike Schatz is with me at Johns Hopkins University. If you're interested in looking up these slides, they're available at the bit.ly link down below. So what is Galaxy, WIGXY for short. So a description of Galaxy that has carried the project for more than a decade at this point is that Galaxy is an open web-based platform for accessible, reproducible, and transparent biomedical analysis. So in practice, this translates to predominantly a web application that has its sort of familiar or standard 3 columns. On the left-hand panel, we have a selection of tools. Depending on Galaxy instance, this is generally in the hundreds of tools available. Once a tool is selected, its sort of web form, tool form representation is displayed in the middle pane, where you can provide the input files, set the parameters for a specific tool, run execute. Meanwhile, you also have help text available for each tool down below a tool. And then in the right-hand panel, we have what we call a history, which builds a track record of your analysis as you progress through various steps. Galaxy automatically keeps up with all the parameters that you have used to promote reproducibility. In addition to being able to run the tools in such a sort of one-off fashion, you can also chain them in multiple steps into workflows. There's extensive visualization and sharing capabilities, and some of this I will show during the live demo. So Galaxy is also sort of a broader thing than a web app. So it tries to meet the key scientific needs of predominantly genomics community, but it has really expanded beyond genomics. So again, as I mentioned during the pitch this morning, Galaxy is a tool distribution platform. So just about any Unix command line tool can be added into Galaxy by creating a simple wrapper around the command that's used to run the tool. 8,000 tools roughly have been already integrated with Galaxy. Many are continuing to be integrated and updated over time. Galaxy also runs a set of services for the world. So usegalaxy.star, as we commonly refer to a set of common or sort of general purpose Galaxy servers available at usegalaxy.org, at .eu, .org.au, .frbe. So there's a number of these servers that are free to use, available at any point in time. In addition to these sort of general purpose servers, there's about 150 public servers that have been stood up by various groups and organizations around the world that promote their own tool sets or specific domains. Galaxy is also supports or part of a large training network. For the past 3 or 4 years at least, there have been over or approximately 100 annual events held at various conferences and whatnot, currently on Zoom. And in addition to these sort of interactive sessions, there are about 200 self-serve trainings available at training.galaxyproject.org that you can do at your own pace, depending on the specific domain you're interested in. And lastly, Galaxy is a vibrant community. So there's thousands of active users each month across all these public servers and the development repositories. This has been sort of validated by through publications. We've reached a milestone earlier this year where we crossed the 10,000 citations mark. And so broadly, Galaxy is sort of composed of its sort of subgroups of communities. So the domain scientists, the developers, the infrastructure providers, and the educators that help run this ecosystem. So it's a very community-driven project. With that, as I mentioned, there's over 150 public servers that are available for anybody to use. Galaxy originally was a genomics platform, but has since then evolved into other omics domains, so metabolomics, proteomics, and other sort of biology-inspired domains, but has also stretched beyond this domain into natural language processing, machine learning, climate change, where people have exercised that ability for Galaxy to integrate just about any command line tool that I mentioned. Galaxy is also part of a couple of large US national infrastructure projects, namely the Anvil and the Galaxy for Cancer, that allow and are integrating Galaxy with protected data sets. And so if, as an individual, if you're looking to start using Galaxy, where do you start? So the easiest thing is just to go to usegalaxy.org and start running tools, exploring what the capabilities are. However, there's many more options. As I said, there's many public servers. There's the Anvil for human genetics and protected data sets. You can install Galaxy locally on anything from a laptop to an HPC system. You can run Galaxy on the cloud on Amazon, Google, Azure, OpenStack, a lot of the open source clouds such as Jetstream or Nectar in Australia. And then there's a commercial version of Galaxy Pro. And if you're more interested, the timing is coincidental, but we're doing a webinar tomorrow that will go across all these options, and you can check it out. It will conflict with this CZI kickoff meeting, however. And so I want to spend the rest of the time on demos. These demos will largely coincide with the capabilities that we plan on enhancing and developing over the course of the next year. So despite the ability for Galaxy to for a user to run hundreds of tools in the context of Galaxy, there's opportunities here to extend the analysis capabilities. So we'll show that. We'll show how to more easily integrate data into Galaxy, and then show how we plan on speeding up job execution, but that's kind of difficult to show in a demo, so I'll refer to slides. Oops, that's the wrong. So for this, I'm gonna, I guess, show up Galaxy for a second in a live format. Again, Galaxy has these three panes. On the left-hand side, you have a large list of tools grouped into categories based on their function. The categories sort of expand and expose the individual tools. If we click on a tool, that's where the tool form is displayed. So as I said, you can choose the input files. So I have two preloaded in the history here that I've just uploaded for the sake of time. Set the parameters, leaving everything unchanged, just leaves the defaults. The overview/help for the tool is available in the tool form itself. Once we hit execute, the job will be submitted to the backend. Galaxy supports execution of jobs on anything from a local machine to an HPC cluster to cloud resources, as I sort of mentioned. So at this point, Galaxy has queued the job, and once the job is running on the cluster, it will get updated. As I also mentioned, Galaxy has this notion of workflows. It has a graphical workflow editor. So in this case, we can look at a simple quality control workflow that allows us to sort of pick the tools from the tool panel, add them onto this canvas, and then link them. So in this case, I can remove this particular connection and link the output of this particular tool or this particular task to the input of the next task, and carry on, again, in this case, providing some quality control analysis capabilities. Once you're happy with the workflow, you can say, well, let's run it. Let's run a sequence of these tasks through a form that looks similar to the individual tool form. Again, I choose the input files that are available in my history. So the original two files that were in the history, I hit run, and Galaxy will now execute these tasks in sequence, in parallel, if possible. Meanwhile, we can see that our previous job has now completed. We can observe the details of the job, or sort of the peak in this case. So we keep adding jobs. We can observe all the properties that were used as part of the tool, again, for reproducibility purposes. That's kind of the general overview of Galaxy. And so where we plan to extend this, well, again, this is great with all the available tools, but what if you want to do something else, something that's not available in a tool right away, and you want to use some scripting? to enhance these built-in capabilities. So for this, we've been working on this notion of interactive tools. So on this, you can see I'm using the test server for Galaxy. This is a sort of preliminary implementation with limited capability, but is technically available. I can run, in this case, a Jupyter notebook inside the Galaxy environment. So again, I can choose the data sets that I would like to import into this environment, hit execute, and Galaxy will now spin up a dedicated instance of this Jupyter environment. So this runs in a container. We here can see that the environment is now available for us to use. And once we access it, we get the Jupyter Hub interface that gives us a choice of runtimes that to choose from, to use. The data that I've selected from the Galaxy history is available in the data folder. So if I look at this, this is the file, the same file that was available in Galaxy, and inside, for example, the Python runtime environment, I can now run. I don't know. In this case, we can just do a simple ls. Oh, I'm in the wrong directory. Sorry. Okay. Well, not to see me coding now. The idea is that you're able to use Jupyter, write your own little shells and scripts, and then integrate them as part of Galaxy and all that. However, there's some deficiencies with this. For example, it's currently not possible to save this. It's not possible to share. It's sort of limited in capability, and so as part of this project, we plan on enhancing this. The other thing that we plan on working on in the context of this project is easing the capabilities for users to bring data into Galaxy. So Galaxy already integrates with a large number of public resources from which you can pull data in. So the sequence read archive from NCBI is one where you can provide an SRI accession. And Galaxy will pull the data in, again, public data. You can upload data from your local machine, either from local computer, from an FTP, or paste public URLs. And again, Galaxy will import those data sets. However, if you have private data sets, for example, in a bucket somewhere, that's currently not possible. So I'll shift over to a different Galaxy server. This one's running on my local machine, and show off some preliminary work that we've done in this space. So again, the capabilities exist for, in this case, a reduced toolset. But here I've added this choose remote files option, which if I click, has been configured to browse a couple of buckets that exist on Amazon's S3 object storage. And here, this is a bucket that's available only to me. I can browse this bucket and select the files. These are fairly large, so I'm not going to import one of these. I've created a simple little bucket with some small files. Again, I can select the file, click OK, initiate that transfer in Galaxy, and it will get transferred. So this is, again, a proof of concept that we've sort of started implementing in the context of this project. However, this is still server-wide, so anybody that has access to the server can browse the same buckets. Being able to do this on a per-user basis is the next step of development and advancements. And now I'll go back to the slides. As I mentioned, we're looking to the third sort of goal is to speed up how we run some of these jobs. As it stands, once the job is submitted to Galaxy, the job execution framework has to fetch the input files, and it has to do this via Galaxy. So it has to ask Galaxy for a data set. The Galaxy has to proxy the data transfer from a backend storage, and via Galaxy, the job runs, and then the data needs to be persisted via Galaxy to the persistent store. So as part of this project, we're looking to eliminate that extra hop and hence speed up the job execution, where a job can fetch data directly from data storage. For example, in this case, if these jobs run on an Amazon cloud instance and this data is stored in S3, they can the jobs can fetch data directly without having to transfer that data to a server where Galaxy might be running. And so lastly, a lot of these capabilities that we plan on advancing are sort of complex, require complex deployment. Version requires a number of services and configurations to operate efficiently. which can take anywhere from days to weeks to set up and then maintain over time. So to ease this, we've been working on this genomics virtual lab platform that codifies best practices for Galaxy deployment to ease the deployment and management, and in turn facilitate the adoption of this complex technology. So you basically get a complete production grade Galaxy deployment without having to learn all the intricacies of all the services that are required to run it. So we will, in the context of this project, we will advance again the genomics virtual lab capabilities to include support for interactive tools and remote data computing. So I think I'm out of time, but there is a video that that we made for how you can actually consume the genomics virtual lab abilities through a simple web form, launch it on the cloud, and have a production version of Galaxy. So the video is available. As I said, the slides are available. The link is to this video is here in case you want to take a screenshot and watch it at a later time. And with that, well, this really wants to play it. I'll close and see if there are any questions or comments about what you've seen.
Is there anything from the Jupyter side of infrastructure that we could do that could help you folks smooth out the integration with Galaxy? Are there any blockages or improvements that we could make on the Jupyter side to make your job easier?
None come to mind, frankly. We're fairly early in this effort, I'll say. So this is so the data transfer is a bit sort of convoluted, I guess, from our perspective. We have to either include the API key into the Jupyter environment so that it can interface with Galaxy. So once we get into that, maybe there's an opportunity there to see if there's some kind of mechanism through which we can ingest the data without having to expose all of users' data. So compartmentalizing which environment has access to a key, because as it stands, once an API key is passed, whoever has a link to that Jupyter environment, they can access any of the user's data. So that's the only thing that really comes to mind off the. But again, early in the process, we'll see. But thank you for the offer. Really appreciate it.
Sure, no, and happy to chat and kind of understand in more detail exactly how that data flows and what we could do to help you guys. So, but great job otherwise. A wonderful talk. Thank you.
Thank you.
Melissa, I think you are up next.
Okay, so hello, I'm extremely glad to be here. My name is Melissa, I'm based in Brazil, and I'm here to talk about NumPy and OpenBlast and to discuss a bit the work that we've been doing that has been made available because of the grant that we received from CZI on cycle 1. And to give you a preview of our plans for cycle 3, which is set to start next year. So the things we are planning to do on NumPy and also on OpenBlast. Our aim is to improve usability and sustainability for both projects. And first, before I talk about the grant and the actions we are planning on doing, I wanted to give you some background. I'm sure many of you, if not all, are familiar with NumPy. But just some information for background. It is the fundamental package for array computing in Python. It supports the whole scientific Python ecosystem. For example, in November 2020, just to give an idea, it has had more than 42 million downloads over PyPI. We estimate that it has around 10 to 15 million users worldwide. It has received around $1.5 million total in lifetime funding, including this new grant. And we count around 10 active maintainers working regularly to keep the package going and the project moving forward. As a foundational tool, it is used in many areas such as data science, image, audio, and video processing, gene sequencing, to list a few. It supports many areas of scientific research and industry, including space exploration, healthcare, finance, and even sports. As a historical perspective, NumPy appeared in 2006 out of a desire to solidify fast array computing in Python. including linear algebra operations necessary for many of the scientific uses of Python. It was built over two competing array libraries for Python, numeric and numarray. Nowadays, many other NumPy-like array or tensor libraries have evolved in the Python ecosystem, including PyTorch, TensorFlow, and many other tools such as Numba and Dask have been developed with NumPy arrays in mind. It is fair to ask if those libraries might in the future replace NumPy, but in fact, the idea of ensuring interoperability with those libraries is in our roadmap and is an active focus of our developers. Also, since I'm talking about OpenBLAS, small information about what it is. OpenBLAS is a highly optimized library for linear algebra computations. It provides accelerated versions of BLAS, which are the basic linear algebra subroutines that all of our computers have, and LAPACK, which is the linear algebra package. The two are the universal interfaces to perform linear algebra in computers. It is a key dependency of NumPy and SciPy, but also of R and Julia. So while most users will not realize they are using it, it is essential for the three leading scientific open source programming ecosystems. So we have had funding for NumPy and OpenBLAS as a joint grant as part of EOSS Cycle 1. And we've been extremely happy with that funding because as you have seen, both projects have been historically underfunded. And so it has really helped, especially because the OSS program is so innovative in the way that it allows you to spend money on things not necessarily related to code. And I think this also speaks to the keynote that we've seen before about diversifying the ways of contributing and opening new pathways for newcomers to join the projects and find their way in order to contribute. So this is extremely healthy for our projects. So what have we been doing through 2020? Over 2020, NumPy and OpenBLAS have been able to do relevant work because of the grant. So for NumPy, we've seen an increase in engagement from the community. So we have been doing periodically, it's actually weekly community meetings where 10, sometimes more people show up and participate. The new numpy.org website has been released, and this has been made possible because a new website team has been formed and is active now. Also figuring out ways to contribute to the project over the website development. There are bi-weekly documentation team meetings, and this is also because a documentation team has been officially established. And we have had a lot of new contributors coming through the documentation team. 2020 has also seen the first NumPy community survey. We've had over 1,200 responses. And while the final report is not yet ready, we are confident that we will take from the survey answers some idea of our community and our users and the ways in which we could maybe improve our roadmap to meet our community's expectations. For OpenBLAS, the cycle 1 of the CZI grant has allowed many improvements in the thread safety code for the OpenBLAS library and support for the 512-bit advanced vector extensions or AVX 512 code. And also because of the increased activity generated by the grant, it has also attracted several new contributors, which is great because there is officially one maintainer for OpenBLAS. And while it is an extremely important piece of infrastructure for the whole of the scientific computational ecosystem, there's one person officially maintaining this project. So it is good to see new movement around it. So just to talk a bit more about some of those points, the new website for NumPy has been launched, and it does a great job of highlighting the features and scope of NumPy. It includes some really nice case studies showing actual applications of NumPy in the real world, including the discovery of gravitational waves by the LIGO team, the assembly of the first black hole image. We'll also discuss this today in the meeting. And the application of NumPy to cricket analysis. So cricket analytics, actually. So it shows a bit about the broad range of applications that NumPy serves. The website also has the infrastructure necessary for translation into different languages, which we thought was really important. And although they haven't yet been finished, we are actively working on them. So it is possible that we'll have a Brazilian Portuguese translation soon. For the documentation, which is where I'm mostly putting my work, I can say that this was a focus of the grant, was improving the NumPy documentation, but I think it has gone beyond that in several ways. So the documentation team has been created with a goal to make the docs documentation contributions to be first-class citizens. This means that people who contribute to the docs are as valued as people who contribute to code or people who contribute to the website, not making a difference between core developers and docs people. This has also been important because we considered restructuring the documentation to make it friendlier, because since NumPy is such a huge project, the documentation is a bit all over the place. There's so much documentation around, but it is mostly API documentation. So we wanted to create a space for tutorials, for how-tos, and user-facing documentation. So first we started with the restructuring, and this resulted in the NumPy enhancement proposal that organizes the ideas that we have around documentation. And then a new repository was created called NumPy Tutorials, which has the objective of lowering the barrier of entry for people who want to contribute to documentation. So the idea of this tutorial, this repository, is that people can submit tutorials as Jupyter notebooks. So they can write their own educational narrative documentation material, submit it as a Jupyter notebook, and we'll take care of the rest and put it into the right format so that it's rendered in the web, and make those Jupyter notebooks available for people to download and test and use them in their own studies. So all of this movement has also helped attract a lot of new contributors, which has been great. We have also participated in Google Season of Docs. We've had 2 technical writers working with us. Each of them has generated around 3 or 4 new documents, as well as helping in other aspects of the documentation, like reorganizing, rewriting. And they are both, so Season of Docs has just ended, but they are both planning on staying with us as volunteer contributors, which is great. So we are very happy with the results that we had, that were made possible by the CZI grant that we received. So we are also very happy to have been awarded the second time the CZI grant. So I'm going to talk just quickly about our plans for 2021. First of all, of course, we want to continue managing the documentation team. This has been helpful for us as a community and has enabled us to diversify the ways in which people can contribute to the project, which is a concern for us, that we make those spaces available. We are also planning a major update for F2Py, and I'll talk more about this in a bit. And we are also planning on addressing key technical issues in OpenBLAS again, since this is usually, if OpenBLAS has problems, it will affect all the other projects that use OpenBLAS. So it is a key piece of infrastructure that needs to be continually maintained and improved. So F2Py, it is actually a part of NumPy and creates extension modules that can be imported in Python. So the idea is that you want to glue fast Fortran code with flexible Python code and enable high-level features such as interactivity and plotting to existing research code written in Fortran. It can be used as a command line tool or as a module. It is a dependency for many important projects, including SciPy, and it can be used to wrap Fortran or C code. However, Fortran has evolved over the years, and although it is considered by some as a niche language, it is still very, very popular among scientific computing and high-performance developers, and it is an active development. But because we haven't had a dedicated maintainer to F2Py in the past years, it doesn't support many of the current features of Fortran. Also, because of limited resources dedicated to testing, regressions have been introduced in the F2Py code that may result in a propagation of bugs for many other projects. So which other projects? I brought a non-exhaustive list of projects that use F2Py directly in one way or another. So for example, there's SciPy, which is tools for working with ocean models and data. WRF Python, which is a collection of diagnostic and interpolation routines for weather research and forecasting. scikit, which is a Python wrapper for routines for systems and control theory. PyHip, I hope I'm pronouncing that right, which is used as a pre-processing step in the geometry and mesh creation process prior to an optimization. SciPy itself, and users who use Fortran, and many more other projects. So what are our plans for F2Py? For the current features, currently F2Py supports wrapping Fortran 77 and Fortran 90 code, except for derived types, which were included in Fortran 90. So to support those modern use cases, we plan to add support to derived types and also work towards full Fortran 2003 compatibility. We also need to work on documentation because some of the features of F2Py are not detailed in the documentation. Some of the docs are obsolete. So we are also planning on writing a new F2Py user guide with comprehensive examples and feature descriptions. A lot of maintenance has to be done, also including testing. And we are happy to bring back Jaro Peterson, who is the original creator of F2Py, back to work on the project with us. And this will be made possible because of the CZI grant. Just to finish, for OpenBLAS, we plan on addressing critical technical issues, including identifying and fixing any remaining bugs in the thread local storage code, in particular at high thread counts, implementing common BLAS extensions like Hadamard product already provided by similar libraries, and identifying and fixing performance bottlenecks at small matrix sizes. And this work will mostly be done by Martin Crocker, who is the current maintainer for OpenBLAS. Thank you. I'd love to hear your questions.
Hi there. Thank you for your presentation and for your work on NumPy and OpenBLAS. I'm Sumana. I'm from the PIP project. I'll just preface this by saying I hope that someone from NumPy or OpenBLAS will come to one of our 6 PIP user experience listening sessions. I have info about that in the Slack. But also, speaking of in-person conversations and live conversations, you mentioned the weekly community meetings, and I'm curious, as someone who works with a project that possibly has a big wide group of users and constituencies, if you could talk a little bit more about how what activities happen in those meetings, what kinds of decisions, if any, get made, and also about how much retention you have, whether it's the same people who come every time mostly, or whether new people show up and there's a lot of churn.
Thank you for the question. Yeah, so we have the weekly community meetings actually alternate between open community meetings where any subject is welcome. Anyone can come in and ask questions or figure out contributions, discuss open PRs if they have questions about them. It's really more of an open discussion. And the other one is a triage meeting where mainly developers discuss open PRs that could be closed or should be closed. Are we accepting this or not? Does this make sense with our roadmap or not? So those are more developer related meetings. Also, we have the documentation team meetings, which are bi-weekly. So and we see that, for example, for the community meetings and the documentation team meetings, um, the audience does vary, but there are like this group of people who keep coming back. So we have a kind of a consolidated group, and then some people come and go periodically. And I think that's the nature of open source contributions. But I think having those meetings face to face is usually a good time to discuss more sensitive topics or stuff that you don't want to discuss over 100 GitHub comments, or things that you can maybe question before you make a decision. I think it's extremely helpful. I think having face-to-face conversations is usually better than using text.
Thank you very much. I have a lot more that I'd love to talk about that with you, but we'll talk outside of this chat.
Please reach out, yeah.
I have perhaps if you can get to two questions, I'll ask them briefly. One is I saw recently that Rust had started using Bliss as a valid BLAS, and I haven't looked at Bliss in a long time, but I was wondering if you folks have been in touch with that team and what the current state of kind of thinking around alternate BLAS implementations like Bliss, because Bliss seemed like a really interesting project. And the second is, how much are you in touch with Andrej Certek and the kind of Fortran Renaissance team that I'm super excited about what Fortran and they are doing. So if you can get to a little bit of those, thank you. But again, it's wonderful to see what you're doing with the project. Thank you.
Yeah, thanks for the questions. I'll answer both because the first one I'll have a very quick answer, which is I don't know. Because I'm not, so I know that Bliss, I don't think Bliss is supported right now by NumPy, but I might be wrong. I don't think it's officially supported. But I know that, for example, some people use MKL, some people use OpenBLAS, some people will use Atlas. I don't think they use them anymore, but yes, I think there's many other competing BLAS implementations, but I think OpenBLAS is like the for us, it's been the common denominator, I guess. So focusing on that. About Fortran, yes, I have been in touch with Milan and with Andre and with a lot of people who have been working in Fortran lately. And I have given a talk at Fortran Con this year. We had our first Fortran Con. And yes, I wish I could have more time to contribute also to the Fortran community, but lately time has been a little scarce because of things happening. But yes, we are in touch.
Rolf, you want to chime in there?
I think the chat says it. I think the Bliss team is, happy to talk, but they only have, I think, 1 or 2 active people. So you can get BLAS, you can't get Layback, and that's a big topic to finish.
And next up is Warren with SciPy.
So yes, I'm Warren Weckesser. I'm one of the developers of SciPy, and basically I'll be summarizing the work we did over the previous year, and we'll be doing it still a little longer for the CZI, the Cycle 1 EOSS. So SciPy is one of the fundamental libraries in the in the Python scientific computing ecosystem. I'll let you go to scipy.org to find the background and also look up the Nature Methods paper from last year, which was a very useful a milestone for SciPy to publish a paper in Nature Methods. But I don't have a long background right now on SciPy here. I'm going to kind of dive into the meat and potatoes of what the work that we did here. I suspect probably many people here already use SciPy, so it probably doesn't need a whole lot of introduction. So the people involved in this project this year have been myself, Matt Haberlin at Cal Poly, We also got, that's a typo, Nicholas McKibben was helping out with some of the boost wrappers, and Matt had a couple students at Cal Poly, Samuel Wallen and Dominic Chamil. I'm not sure if that's the last name. I will also add that I won't do any live demos, but I do have little code snippets. I'll show like IPython sessions to show you. It's just some quick demo, not demos, but not live anyway, but samples of what the code looks like. So the core of our project was basically improving the statistics library in SciPy. SciPy has been around a long time, and therefore so is the sort of the stats module in SciPy. But when we first saw the call for proposals for CZI, we found it seemed like it fit very well, because having used SciPy for many years, you realize there's some pretty big gaps in what's covered in SciPy. And so we kind of went through some basic classic text on statistics and say what is not in SciPy that should be there. And so we kind of picked out a few topics to include as part of our proposal. So this is a short summary of what we kind of focused our work on. We've been adding new probability distributions, also improving the performance and accuracy of fitting distributions to data, and also providing more options for fitting, more flexible options, and more ways to analyze the results of a fitting of a distribution to data. And also, one of the things we're working on is improving some of the underlying code that the SciPy code wraps, some of the underlying Fortran C libraries, or providing better ways to have underlying libraries. We've also added a variety of new statistical tests, and we're improving some of the existing tests. So the typical, one of the ones you see right away if you're using SciPy is that there's almost no, at least like in SciPy up to 1.5, there's no ability to compute one-sided p-tests. And there's no ability to compute confidence intervals. Maybe at one spot we can do a confidence interval for statistics. So we're adding that. We've also enhanced some of the contingency table analysis tools. I will point out that some of the work I'm going to talk about here is actually still in progress. We kind of scheduled our work on this for this grant to go through January. So we have more work still to go in the next few, 6 to 7 weeks still of work to do here. Also, I'll point out that while most of the things I'm going to show are basically from the grant proposal, a couple things that weren't in the proposal I've included here because basically they were effectively funded by the proposal because the reviewers were funded by the proposal. So they kind of got reviewed by us, and they're probably worthwhile including those as part of the product of this work. All right, so I'm going to dive right in now to some just nerdy details of math and stats. We've added several new distributions to stats. We have the negative hypergeometric distribution, negative non-central hypergeometric distribution, multivariate hypergeometric, multivariate T, asymmetric Laplace. This is one of the ones that the Laplace one was not one of our original part of the proposal, but it got worked on because we were being funded to work on SciPy. And this line of code here just as a trivial example of using multivariate hypergeom, the multivariate hypergeometric distribution. And that's, it's a object you get from SciPy stats. It has an RVs method, and you pass in the parameters. So here I'm generating a sample from that distribution. I got 5 samples of this three-dimensional multivariate distribution. And I think actually that's one of the things that has come out of that is that we have some more work to do on some of the code has evolved organically over the years, including our multivariate distributions. And we have a little more work to do still on sort of unifying and cleaning up the API of some of these methods in our distributions. Wrong way. I mentioned we're working on improving the fitting of distributions to data. The default method, we have like over almost 100 univariate continuous distributions in SciPy. And they're written as a class. You subclass a main, high-level class, and the default fit method does maximum MLE, maximum likely estimation, and it uses a default numerical optimization routine to do that. But in fact, many of the distributions have an actual formula you can just plug in to get the MLE, get the estimate of the fit. Or if you do a little bit of work, you can find a much simpler numerical problem to solve than the full optimization problem. And so we've been working on adding some of these improvements to the, improving the MLE, maximum estimation calculations in these distributions by having the formulas themselves will be faster, more accurate fitting calculations. We've already implemented this for quite a few of the distributions, the Laplace, Pareto, Raleigh. There's more in progress. We're also adding new features in terms of how to fit and what kind of results you get from a fit. So for example, the pull request is there. We got some more work on refining it to go still on fitting with the method of moments to fit distribution of data, handling censored data where you, instead of having, a sample value is 15, all you know the value is 15 or greater, or it's in some interval rather than being a discrete value. And also an important thing we want to add, or we are adding, I've got code that I'll show in a little while. It's kind of a good rule of thumb that whenever you create a routine that does a fit, you want to have some way to assess the goodness of that fit. And that's been missing from SciPy since the beginning. So we'll be adding some estimate of standard errors to the fit method. Here's an example of, this is also an example of, I said this is work in progress and some of this stuff. This is not in SciPy, but it will be worked on, very soon and to get into SciPy, but it is part of the CZI work. Here's an example where I've got some data. This is actually from a paper, just an example I found online of, this is an example of fitting censored data here I'm going to use the Weibull distribution. My data is these numbers here, 3, 5, 6, 8, 10, and so on. The star means that number is simply a lower bound for the actual value. You don't know the actual value, it's a lower bound. That's called right censored data. And so and the way I've got my current API set up, when you have censored data, one way to implement that as an API is to give it 2 arrays, one for the left end of your interval, one for your right end of your interval, or whatever your interval is. And so for right censored, you can say the right interval is infinity. So here I have that. I've got data is the array of the raw numbers, and data 2 is for the non-censored data. It's the exact same thing as data. For the right censored data, it's got the infinity in there. So these 2 arrays here define my censored data set. Now I can plug that into the fitting code here, and it will then produce an estimate of the parameters and of the standard errors of those parameters. And again, it's not very exciting to look at right now, just numbers, but that is part of the work in progress that we'll be working on finishing up hopefully in January. So that's one of the bigger features is adding this fitting of censored data and computing standard errors. So another important area that we're working on adding is, I mentioned earlier, is including one-sided p-values for a lot of tests. We've already got code in there for t-tests and Pearson's, and or either committed or in pull requests for the t-tests, Pearson's, product moment correlation, Spearman correlation, linear regression, and a few other tests here that we've got working. Again, a very trivial little bit of code here. This is for a one sample t-test. My data is this array X. I plug it into the t-test one sample, but I say I want to look at the my hypothesis is that the mean is 15 or greater. I plug it in, I get a p-value back. So it's a one-sided p-value in this case rather than the typical two-sided that we've had in before. So that's also ongoing. A lot of the work for this was done by one of the students at Cal Poly. Another one we're working on is adding confidence intervals to a lot of the statistics that are available in stats. This is an alternative. Effectively, it's an alternative to. It's sort of the same, a similar view, but an alternative to p-values. And currently, we have about 4 or 5 tests that we've added the confidence intervals to. Here, I've shown an example of computing, say, a binomial test. I've got a test with a proportion of some data set. So here I've got. If I have a data, I've done a sample where I've got 11 successes out of 55 trials, and I think my proportion should be 1/4. I plug it into the test, and I can get well, in that case, the estimate would just simply be 1/5. 11 over 55 would be 1/5. But I can then ask, what's the confidence interval for that estimate? and I get from about 0.1 to 0.33 as my 95% confidence interval for that test. This again is also ongoing. This is a different example of the Pearson R, the Pearson's correlation coefficient. Same idea. I keep hitting the wrong keys. Same idea. Do a correlation coefficient between x and y. That we have a function called Pearson R, which computes the R correlation coefficient, and we now have, as part of the return value of this function, a method to compute the confidence interval of that statistic. So here, the estimate of the correlation is 0.938, but the confidence interval is from 0.688 to 0.989 or so. So again, these are pretty much very fundamental tools that just have been missing from SciPy for decades. So we're kind of nice to get these in there into SciPy finally. Another important category is contingency tables, and we're adding, expanding the capabilities that we have, what's already in SciPy. We're adding odds ratio calculations with confidence intervals, adding confidence interval for a sample odds ratio. There's this quantity called relative risk. Again, relative risk is very important these days because almost every paper you read about COVID that analyzes, risks of COVID under certain conditions will report a relative risk of some condition or some treatment or some behavior. And also just generic measures of association for contingency tables. So here's an example of computing odds ratio. This is just some table of this 10, 20, 8, 4. That's a 2x2 contingency table. I can do a Fisher exact test. That's been there for a while. We can compute the odds ratio of that table. That's a trivial calculation, but what's new is, I should point out the orange codes here, the orange code text are sort of the new things that was part of the work we've been doing. So the odds ratio for this table is 0.25, just 1/4. But we now have the ability to compute the confidence interval for that estimate. And here we get a confidence interval. Here I believe I did 0.99 confidence interval. And we see the range goes from about 0.039 to about 1.6. And that's just, again, this is an alternative view of p-value. The fact that if this data were independent, if there were no correlations or no associations there, the odds ratio should be 1. And so if 1 lies in our confidence interval, it probably means that there's no, that it's not a significant result, whatever this data came from. This is why I'm showing numbers here for now. We've also added an alternative way to compute the odds ratio, which is the conditional odds ratio, which involves using kind of assuming the marginal values of your table are constant, and then leaves you one free parameter, and then you've got a one-dimensional distribution for the odds ratio. And we've added that calculation and its odds ratio, very close to the same result, a little bit shifted, actually a little bit wider confidence interval for that case. So that's now in there, or that will be in there soon for 2x2 contingency tables. This is an example of computing relative risk. This is just some numbers from actually from a book, also came from a paper. The terminology here, CHD is coronary heart disease. CAT stands for catecholamine. And this is a typical summary of some of experiment or collecting some data on whether or not high levels of CAT are associated with coronary heart disease. And here we take the data, we plug it into the relative risk function with the numbers of sort of the, how many of the high CAT category, how many were a case, how many had coronary heart disease, what was the total, and same thing for the low CAT, how many had coronary heart disease, what's that total, plug it into the relative risk, we get back this number 2.45. That tells you that if you have high CAT, the odds of getting coronary heart disease are about 2.45 times higher than someone with low CAT, low catecholamine. And so we have that calculation. That's a new calculation. That number is trivial. One interesting part is the confidence interval. Again, we get a range of here we get a range of 1.5 to about 3.8, which suggests that this is significant because if there were no association, you'd have a relative risk of 1. So again, more just useful tools to have in SciPy. We've also added
Warren, just to note, you're at 15 minutes here. So just
that I'll kind of it's in there. It's just more ways of looking at what kind of coupling is there between data in a contingency table. We've added this is a new function. This is again a new one that we've been reviewing. It wasn't originally part of the CCI proposal. We've got new tests. We've got, I guess go through this quickly now. Pages L test, which is looking for a test of trend of data. Again, we have a page L. Even that name might change. There's also sort of APIs evolving. We might change the name and so on. But that's in there. We've added the a variation of Kendall's test, which is Kendall's Tau C. Again, one of the core tests in, well, a core test to have, good to have available. We're also adding new tools for analysis of variance. Currently, SciPy has just one function for single factor analysis of variance, the F1 way. We're expanding that to first of all, kind of a more useful output, more output in from the function, and also looking at multi-factor analysis of variance. So here's a simple example of the new version eventually of a ANOVA one-way, where actually, for example, just the output you get is a nice typical analysis of variance table, rather than just numbers like p-value and f-stat. And so that's an example of using ANOVA one-way. This is an example of doing a two-way balanced ANOVA, where I've got data for, I think, data from a biostats text. I can just reproduce that table, that result with this new function, ANOVA two-way balance. Again, it gives you back typical two-way ANOVA analysis of variance table with f values and p values and errors and so on, which is currently not available in SciPy at all. One more important thing that we're working on is a lot of the functions in SciPy are built on special functions, and in the SciPy special functions, that library is built on some legacy libraries such as CDF-lib, which is written in Fortran, and Cepheid, which is written in C. And we often hit bugs in these libraries, typically when we're trying to push the limits of large or small parameters. And then we eventually, at some point, find a bug or find a limitation, and fixing those or trying to fix those can be a challenge because there's some, well, the Fortran code is there. If you want to look at some spaghetti code, you can look in the CDF-lib. And like other code like Cepheid, there's obvious signs of somebody having ported it from single position, double position, and not doing it fully. And so there's sort of legacy issues in these libraries too. We could go and spend time fixing those and or deriving new methods to do better calculations. But there is a library out there already which does a lot of things very well, which is the Boost library, which is a vetted, actively maintained library, which has a very large collection of math functions, including special functions. And so what we're looking at is providing tools to wrap those, to wrap Boost math libraries to use in SciPy, especially for the distributions and their PDF methods and CDF methods and so on, to avoid some of these problems we have in the old legacy libraries. This is work that Nicholas McKibben is doing a lot of work on here. He's doing some great work on generating wrappers automatically from Boost. That should be a pretty cool thing when it's all fleshed out. Okay, and then finally, one bonus thing, which was not part of the proposal, but it's just evolved as a useful tool in developing for SciPy, and that's this library called NumPy, which is a small library of distributions and stats and movement signal processing that's built on top of NP math for multi-precision calculations. One thing that comes out of trying to look at debug some of the code in SciPy or special functions is we might implement a function, but we want to be able to have a unit test with the true value. How do we know the exact value of that function? In many cases, if our implementation using regular floating point values, it might run into numerical problems that we're not unaware of or don't recognize right away. So if we can kind of crank out some NP math code, and set 25 significant digits or 100 digits of calculation, we can test the values with NP math using this library NumPy, go as high as we want for precision, and then convert to a float and get the true value, and then use that as sort of the known exact value, then using our unit tests in SciPy. And so that's been sort of evolving hand in hand with the work in SciPy stats as a very useful tool for having unit tests for our code. And with that, I will stop and see any questions.
And let's move on to Thomas, please.
I'm Thomas. I'm with scikit-learn. at Columbia University. And today I want to talk about 3 items. First, we'll start off with community updates, what's going on with scikit-learn as a community. And then I'm going to speak on the new features we have that we developed in the last year. And that's what we're going to release this month. And lastly, we're going to focus on our history and gradient boosting and the features we have in history and gradient boosting. Throughout the talk, I'll also sprinkle in bits of what we plan to have, what we plan to do in the future. So let's look at community updates. Scikit-learn has many different issues. There's, as of yesterday, there's 1,500 issues and around 745 pull requests. Reviewing these pull requests are quite fun. We have new contributors and that are new and they're doing documentation changes, and they're very, we welcome them and they're very useful to our community. We also have users that are very experienced in the field, and then every time they have a pull request, it's a joy to review them, because once it's in the library and it allows anyone to use it. It's a way to share their knowledge, and it's very powerful in my mind. So to manage this many issues, we have a triage team. We have started a triage team a few months ago, around the spring, and these are the members. They help us label issues. They label issues and pull requests, determine if pull requests are stalled and would be open for new contributors. And they also help close duplicate issues and issues that cannot be replicated. So this is very helpful in my workflow and in our workflow as a team. And it's been very useful for the past 6 months while we had this triage team. On that note, one of the members of our triage team, Reshima, has helped organize a sprint in June. It was held online on Discord, which is a very cool platform for holding sprints. It allows users to pair program. So when organizing, we had users that were experienced paired with someone that's not experienced. And usually the ones that experienced came from another sprint. And so they allowed them to learn from each other. This sprint was developed to increase the participation of underrepresented persons in data science. There were 10 countries that joined. The attendees were split evenly by gender. And I'm going to share these slides with y'all, so you could there'll be many links in this talk, so I'll share the slides with you after the talk. Also in this year, we have a new core developer. We voted in the spring. His name is Christian. That's his GitHub handle. He led generalized linear models, which is in our case, it's the Tweety distributions, and we have estimators for Passant and gamma distributions. These models are useful because they allow a modeler to target different target distributions, and each distribution has different properties, so you could, which is very useful. Examples of these distributions for Passant would be number of events, or the frequency of events. For risk modeling, it's number of claims. For agriculture or weather modeling, it's number of rain events per year. Gamma distributions are useful for time between events, so amount of rain, cost per event, or amount of rainfall per event. We have many useful usage examples of this. We have a user guide, Passant regression, and a user guide or examples for Tweety regression as well. So these are, as you can see from these charts, this graph, this is the original data. If you use something like rigid regression, it assumes a normal distribution. So the distributions of the test data looks more like a normal distribution, while Passant, and I'll talk later about history and gradient boosting, they have a more, the distribution matches more of the data. So let's jump into advanced in scikit-learn. There's a bunch of features. For this talk, I'm going to focus on the ones that we have written into the grant proposal a year ago. To preface this, most of this work is done by Nicholas. He's not with us anymore at Columbia, so he's been funded by this grant for most of 2020. So I'm going to present showcasing most of his work in this presentation. He have worked on something called sequential feature selection, where you start off with 0 features and then you keep on adding more features based on cross validation. There's a user guide. There's and there's an example. To preface this, every time anyone adds a new estimator into scikit-learn, we have to have the code contribution, the code tested, a user guide for someone to understand the algorithm, and an example of how to use the estimator. So like all these things have to be in the pull request for a new estimator to be accepted. So this slide represents around 3 months of work. So it's a bunch of effort and lots of review. Another one that Nicholas has worked on was system having, which is based on, it's one of the sub-processes used by Hyperman for hyperparameter searching. System having is a state-of-the-art method to explore the space of parameters and identify the best combination. A broad overview of this concept is where you start off with resources and you distribute the resources amongst your parameter combinations, and every sequential step of the algorithm, you cut off the parameters that are doing poorly, and then you keep on cutting it off till you get to your parameter set that you want, the parameter sets that maximizes some sort of score. As with the other estimator, there's a user guide, there's a and also there's also an example comparing it to grid search and system having, and this would be provided at the end of the talk with these slides. Nicholas also worked on major improvements to our documentation. Each one of these items also took around 2 months. They were worked in parallel. There's how does random state work in scikit-learn, cross decomposition, LDA, isotonic regression, gradient boosting, the generic gradient boosting without the histogram part, partial dependence curves, and also fast partial dependence curves for trees and random forests. So each one of these enhances the user guide such that if a new user from machine learning comes in and uses our library, they could better understand the features. Because the goal of scikit-learn is to cater, the original goal of scikit-learn was to cater to scientists and non-machine learning experts and allow them to, if they have data and they could take advantage of machine learning, scikit-learn is a library to help them take advantage of these machine learning techniques. So these user guides were, improvements in user guides were very important to our library, and they were, we took quite a amount of time reviewing pull requests because it's a long editorial process. So this is a lot of work, and it was great that Nick did this, helped improve the documentation for these items. Another thing that Nick has provided was he refactored our check estimator and worked on a SLET, which is a scikit-learn enhancement proposal, and where he refactored our code in such a way that it introduced something called validate data. And this introduced a scaffolding to allow scikit-learn to, in the future, which I'm currently working on, is to allow scikit-learn to accept any array types, such as QPy, and which is an ongoing process. And there's many different ways forward from NumPy. There's array module and array function. So there's a long discussion about this. But this is this laid out the scaffolding to allow that to happen. One thing I want to talk about at the is there's HTML representation of an estimator, not HTML. In this case, this is a classifier, which is a pipeline. By default, it's a string representation. It looks very hard to follow. And if one were to set config display equal diagram, you get this nicer representation if you're in a Jupyter notebook. So you could click on them, and then it tells you details about your pipeline, and it's very nice. So like I recommend everyone, if you're using scikit-learn and Notebook, just these 2 lines should be in the beginning of the code of your notebook, so that you could have this interactive representation of your estimator. So this is very powerful. So you could visualize your estimator and your pipeline. Okay. So lastly, I want to talk about the gradient boosting models. They're called his gradient boosting classifier and his gradient boosting regressor. They're based on LightGBM. So the algorithm is 90-ish, 95% the LightGBM algorithm. And we developed it with Python, and it's written in purely Python, and it's very it's the last time when we benchmarked it with LightGBM 2.0, 2.x, it was on par, but with LightGBM 3.0, 3.x, we have to catch up to that, and we're not our performance is not on par with LightGBM 2.x for now. For features that we've introduced in the past year or so, we added missing value support. This is the only estimator that supports missing values natively. So if you give it a NumPy array with missing values, it would handle it. Under the covers, it does it places the missing values in its own bin, and there's many details to this, but it can natively handle missing values. You can also provide a loss function to minimize. In this case, the percent the percent loss, and so it would directly minimize that during its gradient boosting process. And so I shown this in the first one, the original slides, and there's an example of using this in our examples. More recently, this is going to be in 0.24, which is going to be released this month. This is one of my PRs, pull requests. They allow you to specify categorical features, and so the hidden gradient boosting algorithm would now natively support categories, and and the reason why we have this is that it has advantages compared to other encoding schemes. So for this chart, if someone would one-hot encode it, this is the orange, the native categorical support would train faster, and also it also has the advantage that it will perform better than the other encoding schemes. So it trains fast. So it's very powerful in this manner. One of the things we plan on working on is better ways to tell an estimator what is categorical, because right now this is it's a Boolean mask. You can also have indices, but giving a Boolean mask to the estimator is kind of not user friendly. So we're thinking of better ways to pass this feature level metadata along a pipeline, and that's something to look forward to in 2021 or later this month. So those are the things we are planning to work on with categoricals. Okay, so we've recently released the RC. You could try it out by pip installing it to see to take advantage of these new features. There's a link to the release highlights. There's a bunch of new features. We talked about some of them here. So yeah, thank you for listening for this talk, and I'll accept any questions now.
I will ask on behalf of Dan. He says, when creating improving a user guide, what's the process for deciding what constitutes an improvement? If people disagree about how to explain a concept or what to include, exclude in the guide, how does your community adjudicate this?
All right, this does happen from time to time, where we have disagreements amongst even the community and the core members about who is the audience of the documentation. Normally we try to solve this issue by saying that our audience is we have many different audiences, and our audience is not a machine learning expert, but and someone that's has a scientific background, so they understand scientific concepts. And so normally the way we handle this is if if the contributor and the person reviewing disagree, we have more voices. And then after a month or two, we kind of converge to something like that. Usually, we haven't had we haven't had a discussion that lasts too long, but we just have more voices in the discussion, and that's how we usually resolve conflicts when it comes to documentation. What constitutes as an improvement? Almost every week we have a typo. So like anything, even smallest things constitute as improvements. Rephrasing things to make it clearer, it's improvement. And so that's the first part of the question.
Excellent. Sumana has a question.
Hello, Thomas. I'm also going to repeat what I had mentioned in an earlier talk, and I hope that you or someone from your team will come and talk to the PIP user experience folks so that we can improve any experiences your users are having with Python packaging. But the real question I want to ask is regarding your triage team. Do you have a sense why people sign up to triage bugs and what your retention level is? And I'm not saying why in the world would they do that? No. It's more just, it's always interesting and useful to find out what people's ambitions and goals and intentions are when they contribute to a shared project, right? And it can help us understand better how to make that experience appealing. PIP also has a triage team, and I'd be interested in understanding how to recruit people better for that.
Having worked with each individual of persons in the triage team, each one of them has their own motivation. So I can't speak, it's really hard to speak broadly. Some are employed by INRIA in Paris. Some are, they are active in the GitHub issues beforehand, and we invite them to be part of the triage team. So it's a mixture. One of the triage members help organize our sprints, and so she's active in our community, organizes scikit-learn sprints. So we invited her as a triage member. So it's very, when we notice a member being more active, we invite them to be part of the triage team, and in the future, hoping to invite them to be a core member as well. And that's
all right. So speaking as a pretty experienced community manager, I invite you to be systematically curious about why people do these things, right? It's really helpful. When it comes to code contributions, sometimes you can see that people have a specific ambition of making their CV look better or fixing a problem that they personally have or something like that. But when it comes to working on triage, this goes to the keynote that was given earlier, because it's less directly advantageous to their own personal goals in a really obvious way, it's really helpful to find out more about what is it that's succeeding here.
Okay. I'll look into I'll think more deeply about the motivations. Like each one of them has their own motivations, but
right, of course, yeah. I understand that, right? But list even just thinking about that and beginning to understand it in a larger sense, and even writing it up would be helpful, I think, to us as well.
Okay. Thank you.
Any other questions for Thomas?
I could read it. There's a few more. When are we getting scikit-learn from Ralph? When are we getting scikit-learn 1.0? It's getting more odd that the most polished live package in the ecosystem is still at 0.x. There's an issue on this, and we're planning 0.25 is 1.0.
Awesome.
Finally.
How painful was it to convince everyone of that?
Not really. It only took like 6 meetings.
And it's a nice round number. Emma had a question about saving models for a long-term storage.
From Emma, what is the recommendation for saving models for a long-term storage? Okay, so that's I'm interpreting the question to be serializing models. Currently, we officially only support pickling and pinning your version number. we've talked about this around 2 years ago when we had our in-person dev meeting. And we also try to push, and the result of that meeting was that we want to just tell users to pickle. And if they need something more, we push them to use something like, there's one line, I'm drawing a blank. There's a library that serializes by Microsoft that serializes scikit-learn models and allows you to run it on different machines. But I'm drawing a blank of what the model, the library is. But there's, I'll get back to you on that.
Do you mean Cloud Pickle maybe?
Cloud Pickle was developed for JobLib, and it could be used, but it's still Pickle. So you still have to pin the version number and whatnot. And so Cloud Pickle does work, and the usefulness is that it could pickle more things than Pickle. But there's one more library, but it's developed by Onyx. There you go. Developed by Microsoft. Onyx allows you to serialize the model for prediction only, not for training.
Yeah, maybe just a few seconds.
Okay.
So what I had in mind basically is something like state dict, which you can find in PyTorch. So you have your model and you get like a dictionary or some very general purpose Python object with weights or some parameters that you can kind of save somewhere, however you like, and then maybe, I don't know, you can restore it later.
I've throughout the years, I've heard this being mentioned, different versions of this idea where you want to serialize it in something that's a Python object, and then and then load it back up. And we spoke about this, and one of the things that blocks it is that the question is, are we just reinventing Pickle? But I personally think it's nice to have a state, like some sort of state dict, so that you could like see what's in the model, like as a developer, and that's very useful in many different contexts. So I'll try to push harder on this as well.
Thanks, that's awesome. Thanks.
Thank you, Thomas, and thank you to all of the speakers. Really appreciate this. It went very smoothly.